If you need to determine the hybridization of an atom in an organic compound, it's a good idea to go back and review electron region geometry from VSEPR theory, because there's some pretty strong correlations. For sp hybridization, you're going to often look for linear local geometry around a particular atom. So that might look like this. You have an atom with a triple bond on one side and a single bond on the other, or an atom with a double bond on one side and a double bond on the other. For sp² hybridization, you're going to look for trigonal-planar electron region geometry. That is often going to be a double bond, a single bond, and a single bond, or a double bond, a single bond, and a lone pair, or you might have an end-cap type of oxygen, which is usually oxygen, which is a double bond, and then lone pair, lone pair. For sp³ hybridization, you're going to tend to look for tetrahedral electron region geometry. Of course, that's going to be an atom with 4 single bonds around it, but it might also be an atom with 3 single bonds and a lone pair, or an atom with 2 single bonds and 2 lone pair, or an atom with a single bond and 3 lone pair. There are always little exceptions, but this will get you really far. Quick aside about bonds, a single bond is going to be a sigma bond. They are the longest but the weakest, and there can be rotation around them. Then you have a double bond, which is made of a sigma bond and a pi bond. They are shorter and stronger, but there's going to be no rotation around them. And then you have a triple bond, which is a pi bond, which is a sigma bond, and then 2 pi bonds. They are the shortest but the strongest, and there's definitely no rotation around them. For the majority of carbons in organic molecules, carbon is going to be king, and if you find the right hybridization for it, it gives you a big clue for the others. But there's some exceptions when it comes to lone pair and resonance. This one has no lone pair, and there's no resonance possible. So we have to find first our tetrahedral carbons, which are going to be our sp³. That's going to be this one. One way we know is because it has 4 electron regions around it, and they all happen to be bonds. And then we have another one here. Same situation for carbon 6 and carbon 3. We have tetrahedral or electron region geometry. They're all going to be sp³ hybridized. Now that gives us all of the sp³ hybridized. What about sp² hybridized? For sp² hybridized, we're looking for trigonal-planar or flat regions. Now all of this looks kind of flat, but if you look at this in 3D, this would be trigonal-planar, it's sp² hybridized, and as a little crash course trick, you're looking for single, double around that carbon. Same thing for this carbon. So carbons 1 and 2 are sp² hybridized. What about carbons 4 and 5? Carbons 4 and 5 do fit the linear trend. So if we're looking at carbon 4 and 5, we're going to say that those are sp hybridized. For this one, let's start off by finding our sp³ carbons, which are these two, because they're clearly going to be tetrahedral. And then we have some issues because we have lone pair. So let's think about this. If we look at this oxygen and count the electron regions around it, we have 1, 2, 3, 4. This has a tetrahedral electron region geometry. So far it's going to be sp³. How do we know if it's one of those exceptions where it's sp²? Well, we look at the carbon next to it. This carbon is kind of locked into being sp³ because there's no resonance that it's going to want to participate in. We've got hydrogen caps here, and we have a carbon here. So if we have lone pair and there's no real affinity for them to participate in resonance, so they're not going to go left or right, this kind of makes this oxygen have to stay exactly what it looks like, which is sp³ hybridized. We have a similar situation over here with this amine group. This lone pair on the nitrogen is not going to have an affinity to flow toward this carbon to participate in any resonance, and definitely not toward the hydrogens. So assuming that this is going to be neutral, and we're not going to have a charge on this nitrogen, and we're taking it at face value, this nitrogen will also assume the hybridization of the nearby carbon that kind of locks it into being exactly what it looks like. So this is also going to be sp³ hybridized. In this carboxylic acid, we have the carbonyl here. This carbon is going to be sp² hybridized because it does follow our quick and dirty rules of trigonal-planar. We have a double bond here, we have a single bond and a single bond, so that's going to be sp² hybridized. Carbon's usually not going to lie to you, especially if it's neutral. But looking at this oxygen here, we got to do a little bit of thinking. First thing to think about is, can it participate in resonance? And also, what's the hybridization of the carbon that's nearby? This oxygen has 1, 2, 3 electron regions, so that's one clue that it's sp² hybridized. Plus, this carbon itself has the hybridization of sp². So we have the oxygen and we have the carbon. This oxygen is going to be sp² hybridized. But we have another oxygen here, and this is where it can get a little tricky. because this oxygen can theoretically participate in resonance, but it's going to be a minor contributor. So if we look at what it looks like at face value, we have 1, 2, 3, 4 electron regions. So it's sp3 hybridized. Is it going to be an sp2 exception? It is next to an sp2 carbon, but if you're thinking about this at face value and not assuming it's going to have a charge, we're going to say that this is going to remain, or going to be, sp3 hybridized. However, sp2 can be a minor contributor because it is technically a potential resonance structure. This is just the most common form, especially if you're looking at this on paper and not assuming it's in a biological system. So that's how those work. Let's keep going. Take a look at all of these carbons and you'll notice that they are all going to fit our trigonal planar geometry, which is a huge clue that it's sp2 hybridized. So we're going to go ahead and mark those carbons as sp2 hybridized, all in that benzene ring. We have one here as well, and we have one here, and one here. That's a lot of sp2 hybridized carbons. We also have a carbon-hydrogen end cap over here, so that's a clue that this carbon is going to be linear in its geometry and sp hybridized, as would this carbon be. What's going on with this oxygen? If you count the number of electron regions around it, we have 1, 2, 3. So that's a clue that it's going to be sp2 hybridized, and the carbon that it's attached to is sp2 hybridized as well. So we're going to go ahead and mark that this oxygen is sp2 hybridized. When you see lone pairs, you got to stop and think. So this nitrogen has a lone pair, so we can count the number of electron regions around it, 1, 2, 3, 4. So it's giving tetrahedral, which is sp3 hybridized in this case. However, is it going to be an exception? Are these electrons going to be delocalized or not? Which is basically another way of saying, are these electrons going to have the affinity to flow somewhere else? Can they even? Not really, because you can think about the fact that this CH2 is kind of like an end cap. It's not going to accept electrons going to be going to that region of it. And that's kind of about all the options it has, because this benzene ring is pretty stable. It can have its own kind of like exclusive club of resonance, but there's really no affinity for the electron to flow into that, especially kind of so far away. So because of that, if we look just at how many electron regions are around this nitrogen, we have really no choice but to give it the electron region or the hybridization of sp3. The reason that it's not sp2 is because these electrons are not going to be delocalized. They're not going to have the ability really to flow into any other direction. So they're not going to be delocalized. It's going to just be exactly what the electron region geometry looks like. For this one, let's go ahead and clearly mark the trigonal planar carbons. That's going to be this one, and this one, and this one, and that one. So those are all going to be sp2 hybridized. Those nitrogens can always give us a little bit of trouble here. So we saw that when this nitrogen here had a lone pair, it was not going to be delocalized, so those are going to stay on the nitrogen. But here we have nitrogen in a ring, which is a huge clue, especially since these nitrogens are next to sp2 hybridized carbons. That gives us a huge clue that these lone pair on the nitrogen can participate in resonance. So since they're in a ring with quite a few other carbons that are sp2 hybridized, we're going to go ahead and mark these nitrogens as sp2 hybridized as well. So they're kind of locked into this ring shape, and that means that you can't just look at the electron region geometry. You also have to look at the neighboring carbons. And these neighboring carbons are certainly sp2 hybridized, so it adds extra influence on these nitrogens also being sp2 hybridized. Let's practice with this molecule, which is an antifungal medicine. So look at this carbon. If we're looking at our rules here, it does fit, that would be trigonal planar in terms of geometry, and sp2 in terms of the hybridization. So you could take a second to guess, and it would be sp2. The reason that it's sp2 is because we have a double bond, a single bond, and remember, for organic molecules, we can hide hydrogens. We know that there is still technically a hydrogen here. We just hide them for organic molecules. Not all the time. Sometimes we show them if we want to, but they're not totally necessary to show. Now, let's think about this carbon. This carbon is at the intersection of three types of bonds, or at three electron regions. We have a double bond, a single bond, and another single bond. That fits sp2. Now, for this carbon, we only see two lines, which means we have two hidden hydrogens, but that's still a total of 4 bonds. And since there's no double bond there and there's no lone pairs, we are going to say that it is sp3 hybridized, and it is. This is going to have a tetrahedral local electron region geometry. What about this nitrogen here? This nitrogen is a little interesting because we don't explicitly see lone pair, but you might want to get in the habit of recognizing where lone pair would be if you're not explicitly shown. So lone pair are going to go right there. Now we can count up our electron regions. 1, 2, 3, 4. Is this going to be an sp³ or an sp²? This is going to be sp³ because these electrons are going to stay with the nitrogen. They're not going to have any affinity to flow because neither of these carbons that it's connected to are going to be sp² hybridized. There's really no room for resonance here. For number 5, we see that we have the criteria for trigonoplanar, and we have this kind of geometry going on, so that would be sp². For number 6, this is where it's most clear to see. We have a carbon and a carbon with a triple bond between them. This is linear, and that's a big clue that it's going to be sp. So that is, as a reminder, sigma, pi, pi when we have a triple bond. Now for number 7, we have a carbon with clear bonds that are all single bonds. So that's definitely going to be sp³ hybridized. And then for number 8, if you were to draw out the lone pair on the chlorine, you would see that this is going to have 4 electron regions, sp³ hybridized. And it's very clearly linear.